Good morning, friends and dear students. I feel immense pleasure to be here again for my course Engineering Thermodynamics. Today I am in the topic of Mollier Chart and psychrometric properties. In my previous lecture, I have discussed about the PV diagram, TS diagram, HS diagram, and also PVT surfaces. Also, I have discussed about Rankine cycle on HS diagram, how these things are happening. These things I have discussed. In today's lecture, I am going to discuss about Mollier charts, psychrometric properties, dry bulb temperature, wet bulb temperature, and the dew point temperature. So we have already covered what are the syllabus in the previous lecture. Pure substances, in that we were having the three phases, that is the solid, then liquid, and third one is the gases. And how we can find out if this is your solid, this is your liquid, and this is your gas. So in the solid, they are very, very tightly packed. All the molecules are very, very tightly packed. They will not move to each other. They are in a very nice pattern. It is called lattice pattern. And their spacing is very, very less. They can only vibrate. They cannot move from its equilibrium position. This is the solid. If you say about the gases, it is liquid. And this is the gas. So if this is the liquid, so these molecules are spaced in a very systematic manner, but the space is much more than the solid. They have their own shape. They can change the shape, but they cannot randomly move here and there. So they are not vibrating like the solid. They are not in the lattice pattern. However, they have some specific shape. As and when you put anywhere, they will form the shape of that container. But if you see the gases, they are very, very far away. They will move here. They can move any direction. They will hit the wall, and this is called the gases. So then we have the phase transformations. How transformation of the phase? We have seen this PV diagram of two-phase system. So here is the gas, this is the two-phase, and here we have the liquid. Here we have the solid and vapor system, like water. So here you have the ice, here you have the vapor or steam, and here you have the liquid, water, and here you have mixture of water and the liquid. So this is called the transformation of the, and if you see the TS and HS diagram, TS means it is the temperature and the entropy, and if you see here, but in this, the area of this plot shows the heat transferred, like del Q is equal to TdS. But if you see the HS diagram, very nice observation. In this HS diagram, the vertical line like this, 1 to 2, this shows that H2, and this is shows the H1. So work done is equal to H2 minus H1. Also heat del Q is equal to H2 minus H1, and we know by the first law of thermodynamics, del Q is equal to del W. So if you know the del W, you can find out the heat, and if you know the heat, you can find out the work done. So like this, it is very easy to understand by the HS diagram, and this HS diagram is also called the Mollier chart. So we will be discussing in today's class, so what is the Mollier chart and what is its importance. This gives a lot of information in one go. So that is the beauty of this HS diagram or the Mollier chart. We have also discussed about the PVT surfaces. So in a one plot, we can find out the pressure, volume and the temperature. If the temperature is varying, what will happen to volume and the pressure, and vice versa. Any of these parameters, if you vary, the different other parameters you can find out. We have also find out the triple point at critical state properties and dryness fraction X, and these things we have already seen in my previous lecture. So now I will go for the next very important thing is a Mollier chart or the HS diagram. So an enthalpy H and entropy S chart, also known as the HS chart or the Mollier diagram, plot the total heat against entropy, describing the enthalpy of a thermodynamic system. So it is directly informing about your how much heat is added, how much heat is removed, how much work is absorbed, and how much work is delivered. All things you can find out by the help of the Mollier chart. This chart covers a pressure range of 0.01 to 1000 bar and temperature up to 800 degrees Celsius. It is there in the chart. It is advisable to use steam table or the Mollier chart directly for easy and accurate estimation of the properties of steam, such as pressure, temperature, specific volume, enthalpy and the entropy. So these 5 properties you can find out by the help of the steam table or Mollier chart, which is also given in the steam table as an annexure at the last of the steam table it is mentioned. So it is very easy to calculate these properties of the steam or any other refrigerant and other gases also. It is not only the steam, but you can find out the pressure, temperature, specific volume. So pressure P, temperature T, specific volume V, enthalpy H, and the entropy small s. So all are the specific values, not the total values. So in this, if you want to find out the total, you multiply by mass. So multiplied by mass, you will get the total value. So here I want to show one example how to represent your values on the Mollier chart. So here state 1 at 5 bar and 200 degrees centigrade. So state 1 is given at 5 bar and 200 degrees centigrade. It expands to 0.2 bar. Find the state 2 and net change in enthalpy. So you can see it is a Mollier chart. So here in the vertical axis you have the enthalpy here. Enthalpy, and here you have the entropy. So here this you can see here that we have to, these are the temperature lines, these are the temperature lines, it is all the green, these are the temperature lines. So temperature is given 200, so we have to see that it is a 200 line. Then 5 bar, so here you will see the bar and it is given the 0.01 bar to 800 bar we can give here. So these are the pressure lines. So you see that 5 bar line, it is coming from here like this, and it is, and this is the temperature line. So we can find out this point. This is the state 1, and here we will get H1. Next it is telling that it expands to 0.2. Expands, it is isentropically, means vertical up to 0.2 bar. So here 0.2 line you see, and we have to put a vertical line, we will find this. So find the state 2. So state 2 we can find out X, we can all other parameters. Pressure is already given, we can find out the V, we can find out some other things, T2, V2, X2. All the things we can find out. We can also find out the work done. Here H2 minus H1, this is the work done. Or here H1 minus H2, and del Q also is equal to H2 minus H1. So like this, we can find out all the parameters by the help of the Mollier chart. So here we should see that temperature line, the pressure line, specific volume line, all lines are given. Two parameters will be given. So by joining two, the intersection of these 2 points will be the state 1, and from here it is expanding. Expansion is isotropically. So a vertical line we have to draw downwards. Expansion means enthalpy is falling down. So from H1 to H2 going down, and where it will go up to 0.2. So it will fall here and you will get here. So from here you will get H1, you will get the H2, and H1 minus H2, it is the work produced by this system by doing this. So like this we can find out, and these are the dryness fraction. So here it is 1, this may be 9, this may be 8, this may be 7, this may be 6, 0.6. Like this you can find out what is the state of your substance. Okay, because about this, here is a dry saturated, but here it is a wet, and it is somewhat 0.95. X is equal to 0.95. This you can find out in the real table, all the state of the system. Now another example is given here by the help of this plot. A steam is at 2 bar and 120 degrees centigrade. So state 1 is given that pressure P1 is equal to 2 bar and T1 is equal to 120 degrees centigrade. So state 1 is given. It expands isentropically to 0.05. So P2 is equal to 0.05 bar. So that it reaches to two-phase region with a dryness fraction of 0.8. So X2 is equal to 0.8. So in HS diagram. So first, if you can see here we will see the 2 bar and 120. So here it is a 120, and here if you see this is the 2 bar. So from here if you draw here, and from here this is the intersection, you got this line. So you got here, this is the H1A, I am writing H1, and from here it is isentropically expanded up to 0.8. So here is 0.8. This 0.8, in this line you draw vertical line from here to here like this. So you got this 0.2. So here you got H2. So this you can see, and you can get work done is equal to H1 minus H2. So from here, okay, you can find out this value and this value, and you will get the work done, and you can also get the Q. This will be how much heat is added and how much heat is rejected. So like this you can find out by the help of the Mollier chart. I think it is very much clear, and if any doubt you can ask in my comment box. I can describe it. Now I will show this with the help of the Carnot cycle. So PV and the TS diagram of a Carnot cycle. So in the Carnot cycle, we know that the reversible isothermic expansion, that is the 1 and 2 is reversible isothermal expansion. 2 to 3 is reversible adiabatic isentropic expansion. This is the expansion. Okay, so here is heat added also. Then 3 to 4 reversible isothermal compression, and here is heat rejected. Oh sorry, it is 1 to 2 is heat added isentropically. 1 to 2. Then 2 to 3 is expansion. 3 to 1 is heat rejected. So here we can write is 1 to 2 is heat added at constant temperature. Now 2 to 3 isentropic expansion. Then 3 to 4 is heat rejection at constant temperature. Then 4 to 1 is isentropic compression. So this you can see here that in this we are adding the heat, that is the QH. In this it is a QL, the heat is rejected. In this it is a QL, it is a heat rejection, heat addition. Here this work done, work absorbed. So this is a Carnot cycle in the TS and the PV diagram. Like this we can draw it and we can explain by the help of the. So now I will discuss about some new terms about the dry bulb, wet bulb and the dew point temperature. So we can see here that the dry bulb, wet bulb and the dew point temperatures are important to determine the state of humid air. So for the refrigeration, for air conditioning, we should know this all three types of temperatures, that is the dry bulb, wet bulb and the dew point, and it indicates that how much humidity is there and how much is required for each and every person who is occupying this room. The knowledge of only two of these values is enough to determine the state, including the content of water vapor and the sensible and the latent energy, that is the enthalpy. So out of this dry bulb, wet bulb and the dew point temperature, if we can get any of the two, we can find out the state of the condition of the gases there. So first one is the dry bulb temperature. It is TdB. It is dry bulb temperature, dBT, usually referred to as air temperature, is the air property that is most common used. So it is the air property that most commonly used, refers to the ambient air temperature. It is called the dry bulb because the air temperature is indicated by a thermometer not affected by the moisture of the air. So it is indicated by the pure thermometer which is not affected by the moisture of the air, can be measured using a normal thermometer freely exposed to the air but shielded from radiation and the moisture. So if you take this is thermometer and if you put like this indicates that how much temperature is there, and if there is any moisture is put affected in the atmosphere, this will give the dry bulb temperature. The dry bulb temperature is an indicator of heat content and is shown along the bottom axis of the psychrometric chart. So if you see the psychrometric chart, this will be shown at the bottom of the chart. That is called the dry bulb temperature. Constant dry bulb temperatures appears as vertical lines in the psychrometric chart. So in the psychrometric chart, the vertical lines will show the constant temperature, that is in the psychrometric chart. Now we will see the wet bulb temperature. So we have the three type: dry bulb, wet bulb and the dew point temperature. So wet bulb temperature, it is called T wet bulb WB. So the wet bulb temperature is the temperature of a adiabatic saturation. So it is temperature of adiabatic saturation. This is the temperature indicated by a moistened thermometer bulb exposed to the airflow. So this is the temperature in which a moisture is put on top of the thermometer, and whatever the value it is reading, that value is called the wet bulb temperature. Wet bulb temperature can be measured by using a thermometer with the bulb wrapped in wet muslin. So a wet cotton or wet something we have to put it, and after that how much temperature it is reading, that indicates the wet bulb temperature. The adiabatic evaporation of water from the thermometer and the cooling effect is indicated by a wet bulb temperature. So in this adiabatic, how much evaporation, adiabatic evaporation is taking place on the water, and this also indicates how much cooling effect is there. It is indicated by wet bulb temperature, lower than the dry bulb temperature, and this always will be lower than the dry bulb temperature. The rate of evaporation from the wet bandage on the bulb and the temperature difference between the dry bulb and the wet bulb depend on the humidity of the air. So how much humidity is there? According to the humidity, the temperature difference between the dry bulb and the wet bulb will be persisting. The evaporation is reduced when the air contains more water vapor. So evaporation is reduced if the water vapors are more. The wet bulb temperature is always lower than the dry bulb temperature, but will be identical with 100% relative humidity. If there is a very up to 100% if relative humidity is there, the air is at the saturation line. So dry bulb and wet bulb will be the same value. Combining the dry bulb and the wet bulb temperature is a psychrometric diagram or Mollier chart, gives the state of the humid air. So if we plot on the psychrometric chart, we are going to get about the psychrometric chart. So we will get the state of the humid air. So how much humid air is present, that we can find out by the help of this dry bulb and the wet bulb temperatures. Lines of the constant wet bulb temperature run diagonally from the upper left to the lower left. So this we will see in detail about this wet bulb and the dry. So in this, right in the psychrometric chart. This I have here depicted that if you see here, the air is flowing. There are this is the dry bulb and this is the wet bulb. So why it is called wet bulb? Because here we have put some bandage or some cotton, and it is a wet cotton. Wet cotton, if you just put how much it is reading, that is your wet bulb temperature. And if it is not there, only this air is entering, so this is called the dry bulb temperature. So here if you see the psychrometric chart, so here is the moisture content kg per kg of the dry air. Here you have the enthalpy at saturation, kilojoule per kg of the dry air. Here is the dry bulb temperature. So it is in horizontal, and if you see here, the different lines are here, and these lines will represent from here. This you can find out about these lines. These lines, this will represent this enthalpy minus 250 kilojoule per kg of dry air. So like this, psychrometric charts are there in this dry bulb and wet bulb temperature. So dry bulb temperature at the horizontal line, and from here these are the wet bulb temperature. Wet bulb temperature you can find out, and from here you can find out how much enthalpy, and if you know the enthalpy, you can also find out that how much it is heating or the cooling, because for the air conditioning we need the heat rejection, how much percentage of heat is rejected. So this we will be discussing in detail about in the next classes. Now next is the dew point temperature. So there are three major temperatures in this psychrometry, that is the dry bulb, wet bulb, and the dew point temperature. And you know what is the dew? If you see a bottle, a cold drink bottle, and you take out from your fridge and keep it on the table, after some time you will see that on above this bottle you will see some moisture is condensed. That is called the dew. You can see in the winter season on the field, the grass and other your crop, you will see lot of small drops are found. Those drops of waters are called the dew. So, but what is the dew point temperature? That is a technical issue where we have to understand about the dew point temperature. The dew point is the temperature at which water vapor starts to condense out of the air. So, in air always some water is there, and if it is cold weather, the water will be extracted from the air. Air will be dry, but these waters are dropping on the earth, on the plants. Those are called the dew. So, the dew point is the temperature at which water vapor starts to condense out of the air. The temperature at which air becomes completely saturated. Above this temperature, the moisture will stay in the air. So, above this dew point, moisture will be inside the air. The drop will not form. So, in the cold weather only, this phenomena will occur. If the dew point temperature is close to the air temperature, the relative humidity is high. So, if the dew point temperature is close to the air temperature, the relative humidity is high, and if the dew point is well below the air temperature, the relative humidity is low. So, this dew point is indicated that how much is the relative humidity is present in the atmosphere. So, if moisture condensation on a cold bottle from the refrigerator, the dew point temperature of the air is above the temperature in the refrigerator. So, if the dew point is above, then only this will happen. The dew point temperature can be measured by filling a metal can with water and ice cubes, stir by a thermometer, and watch the outside of the can. When the vapor in the air starts to condensate on the outside of the can, the temperature on the thermometer is pretty close to the dew point of the actual air. The dew point is given by the saturation line in the psychrometric chart. So here, how to find out? Here is the ice and some water. It is put here. You take a thermometer and inside you enter the thermometer and stir it, and after stirring, when the moisture start forming here on top of the container, the air moisture will be sticking there. So that temperature at which the moisture of the atmospheric is start condensation, that is called the dew point temperature. Okay, so dew point temperature is very important because it gives the relative humidity, and this humidity will affect the human and the occupant of any refrigeration system. Next, we will be discussing about specific humidity, relative humidity, saturated air, vapor pressure, degree of saturation, adiabatic saturation, carrier equations, and psychrometric chart. This we will be discussing in our next class. Hope this you have understood well about dry bulb, wet bulb, and the dew point, and what is the importance of this. They are mostly used for air conditioning purpose, because in the summer, if you see near the seashore, you have huge amount of humidity. This humidity is not good. It is creating additional effective temperature on the human, on the surrounding. So we have to make sure that we are in the proper humidity so that a human being will be in the comfortable position. These are the references. That is the P.K. Nog, Engineering Thermodynamics, Tata McGraw-Hill's, Eunice Senegal, Michael A. Bowles. Then Engineering Thermodynamics by Mishra, IIT Kanpur, lecture, NPTEL lectures. That is also very useful. You can go through on that. Any questions, you are welcome to ask. My email is ydwedi@gmail.com. Please do like and subscribe my channel. Thank you very much. Till then, goodbye and see my next lecture on the engineering thermodynamics.
Like, share and subscribe. Hit the bell icon for more updates.